All right, let's do this. Okay, I want to start with actually scratch that. I want to start by getting this thing to not bug me so much. Much better. All right, let's get started. So I want to start with a quick IntelliJ demo. You're going to go over this in lab next week, but I want to do at least a quick demo for those of you getting eager to get started with it. So I got to reset my brain here. I'm thinking at the end of the lecture. Got to rewind 50 minutes. So with the lecture code, all the lecture code is in this repo right here. And I want to show how to clone this repo and get this code in IntelliJ. This is the same process you're going to use for the homework assignment. You're going to find a GitHub link just like this one in the homework doc, and then use that link to clone the code and get it into your IntelliJ, and then edit that code to start working on your homework. So I'll give an example with these slides. You're going to click the link. You can ignore everything here, except this code is going to give you a link. I'm going to copy this URL. I'm going to open IntelliJ. So once you have IntelliJ downloaded, you can either use Community or Ultimate for this course. Community will be just fine for you. It's the free version, and that'll do everything you need it to do for this class. I do recommend the Ultimate version. You can get it for free with your EDU email address. You get an educational license, and you can use Ultimate for free, so why not? Then you'll have extra features that we don't use in 1.16, but then you'll have it set up for future semesters, your future career, anywhere that you'll want those features. They'll already be there for you, and you only have to set up IntelliJ one time. So it can be helpful in the future, or even this semester if you want to work on something outside of class that you can benefit from IntelliJ. So when you first open IntelliJ, you'll get a screen that looks like this, except you won't have projects here. You're going to click Get from Version Control Software, VCS. You're going to get a dialog like this and paste that link that you got from the GitHub repo. And then you'll just click Clone. I already used this default directory that it's going to create because I already cloned this, and then I cloned it again for the previous lecture. So I'm going to put a -3 here. Click Clone, and then we wait. That's going to set up the project. It's going to download all the code and get everything ready for us to start using this code. Might take a little bit to get everything for IntelliJ to figure everything out. And then we'll see that we have the project directory, whatever you named it, probably just class example code alpha. We meant to change the name of this repo before the semester started. So you'll just get this class example code alpha is the repo name. And then you'll see that SRC directory that I was talking about last time. This SRC directory is the source directory. It's for all the source code of the project. And you'll see all the packages that will go use throughout the semester. Week 1, the one that we saw. And then that'll have the files that we've seen. And we'll get probably some form of this error when you first download this. When you first install everything and clone it, it says, hey, your Java is all messed up. You can either click Configure here, or if this dialog doesn't pop up and you have all kinds of errors, go to File, Project Structure, and it's going to tell you to set your SDK to set up your SDK. We want to set this to Open JDK 19. You won't see it in this dropdown yet. You should just see this Add SDK and click Download JDK. And then the default option, once it figures out what it's doing, the default option will be Open JDK 19.0.2. That's the version we're going to use, version of Java we'll use for this course. We're using that version because it's the default with the current version of IntelliJ. It should be the one it recommends and says, oh, you're using Java? Use this. So we don't have to worry about version numbers and differences of versions and everything. So Open JDK 19. The current version is 19.02. Download. And then that's set as your version of Java for the project. And I just learned in the last lecture because I got this error. These are fake errors this code will run right now. But if you still see errors, go to File, Invalidate Caches. And that'll get rid of those errors. Those are fake errors, though. They're shadow errors. They don't actually exist. But IntelliJ thinks they exist because once upon a time they did. And then when we're ready to run code, it's up too high. When we're ready to run code, you'll either right-click on the file and click Run. Well, we got to wait for a progress bar first. We're going to right-click the file and click Run, or right next to the class name, there will be an arrow to run as well, and you run the program. That's going to both compile and run. Compile is a word we haven't really talked about yet. We don't quite have time to get into it today. But this is going to run your code, print hello Java to the screen. And now after you run your code, you can click this button up top, the Go button up top. That's going to run the last thing that you've ran and rerun it again. So once you run once, you'll have access to that shortcut button, but you have to at least one time run either here, here, or right-click in here to run your code for the first time. And then this is a full IDE, meaning this is an integrated development environment. It's everything you need to be able to write code. So if we want to change this to world, if you don't like that I said Java instead of world in the hello world example, we change it, and once it runs, hello world. So you can edit your code, you can run it if you want to play with the lecture examples. If you're wondering when you see loops today, hey, what would happen if I set it up like this? Change it, clone the repo, get it in IntelliJ, change it, run it, see what effect your change had. And if you've already started IntelliJ, you're in a project like this, maybe you created a new project or whatever, if you go to, and you want to clone a new repo, go to Git, Clone, and you'll get that same exact dialog box we got at the beginning that we clicked from the initial splash screen of IntelliJ. So, if all that was too much, that was 7 minutes of setting up in IntelliJ. That's too much, which probably was. Next week's lab, an hour and 50 minutes. The entire lab is dedicated to helping you get IntelliJ set up, clone code, start writing code, and edit code. Get everything set up with the right version of Java. The TAs, you have 3 TAs in each lab. You have 3 TAs to be able to help you throughout an hour and 50 minutes to be able to make sure that you have IntelliJ set up. So take advantage of that. Unfortunately, I don't have more time to do it in lecture to go through like a whole lengthy tutorial, but I at least wanted to get it in lecture somewhere. So any quick questions on that? It's fine. This lecture seems to not want to use it, but I do have Discord open. I'll still have it open in case y'all want to start using it. I think it's 1 question per day on there in this lecture. Okay. Shut this down. Oh, that's another way to get to the splash screen. Just close your project. The splash screen will come back. All right, we have slides that were posted last night. If you don't see the slides link on the repo, I can't demo this because I already did it last lecture. But if this is still inactive, like Monday slides, just hit it with a refresh, and then it'll be active. So if you don't see the slides when lecture starts, they are there. Just hit the refresh if you haven't refreshed the page in a while. Let's do this. We're going to learn conditionals, loops, and loops today. 2 different types of loops. So today and continuing to Monday, we're still going to be in 1.15 content, and then Wednesday we're really going to start the 1.16 content. Though I'd argue that there's some 1.16 content in these lectures because we're doing memory diagrams, yes. But let's jump into it. Conditionals. Again, and I'll probably say this way too many times this lecture, but a lot of this I assume you're familiar with from 1.15. I assume you know how conditionals work, the difference between if, else if, and else, And if I deleted one of the else's here and just had if in the middle, how that would vastly change the behavior of this code. I assume you're all familiar with that and you know how conditionals work. The syntax of how conditionals work in Java, I do have to focus on. It's very similar to the syntax of JavaScript. That is just a kind of a coincidence. So Java and JavaScript syntax are more similar to each other than Java and Python syntax. Python syntax is a bit different than other languages, but that is just a coincidence. Java and JavaScript, despite their names being similar, are completely different languages, as even just from one lecture, I'm sure you found out already. Very, very different languages. But they do have some similar syntax, but that syntax is pretty common across most languages. And Python is kind of the odd language out that has different syntax. Python does things quite a bit differently, for better or worse. I think for the most part it's for the better. But Python does things differently, and the only reason Java and JavaScript are sounding kind of similar so far is just because they do things the more traditional, standard way, whatever you want to call it, that a lot of languages do. So with that said, braces for your code blocks, for your conditionals, and you have to have your parentheses around each Boolean expression for the conditionals. That's really all the syntax stuff that I really have to say. I don't know what else to even say here. So let's jump right into a memory diagram. Memory diagram kind of is the new thing. You know how, you know that conditionals work. You know what they're going to return. If I show you this program, like any one of you could look at this and say, this is going to print ACF to the screen. I would hope at least. Tracing through, even if you don't know the Java specific stuff, that you'll be able to see that's what's going to end up happening here. But as with all of 1.16, we want to focus on how this program gets that job done and what exactly the computer does when it runs this code. So to that end, let's see another memory diagram. Today we're going to see two big old memory diagrams. It's going to be the two examples for the lecture. And last time we started with putting variables on the stack, printing things to the screen. I assume that you're all good with that. Like if I had another example where I just put a bunch of variables on the stack, I would hope that you'd be pretty bored. And I just printed a bunch of things to the screen, you'd be pretty bored. Like that stuff's pretty straightforward, I believe. So we're going to jump right into a stack frame. Stack frames are a little more tricky. I don't think they're overly difficult to follow as I'm lecturing. But remember, you have to get to the point where you can draw these and remember all the details that you have to have in these stack frames. For your quiz, you're going to get code more complex than this, but you'll get code and you'll have to trace through all of the stuff and remember all the steps that I'm doing. That gets a bit more tricky, which, not to get too sidetracked, but that's kind of I'll call it a feature, I guess, of a lot of programming classes. It's usually easy to follow what's going on the projector, and then you get to the keyboard and go, okay, now I have to write a function that does X, Y, and Z. And then you just panic and have no idea what to do. It's very common. Don't worry if that happens to you. That's common. But yeah, let's just get into it. So we're going to have a method call, and we're going to see something new we didn't see on Wednesday. We have a method call that returns its value to a variable that is being declared on the same line. So last time we were replacing the value in a variable that was already declared. The variable was already on the stack. And then the method returned into that variable and added the value, updated the value in that variable. Here we have a variable that doesn't exist yet. It's being declared right now and being assigned the return value of the method. When this happens, we're going to add the variable name to the stack, even though it technically doesn't exist yet. We're going to add the variable name to the stack with no value. Its value is going to be there after our method returns. With no value, but we're going to add the name to the stack, mostly so we have a place for our return arrow to point to. So we're going to draw our stack frame. We have a method call. We're going to draw our stack frame. This is an isolated portion of the stack that cannot be crossed. When we're inside a stack frame, inside that method call, we only have access to the portion of the stack within that stack frame, which means we only have access to the variables inside that stack frame. Inside the stack frame, we can't access this variable result. Well, actually, it doesn't exist yet anyway, but we can't access anything outside that stack frame. We're going to put the name of the method being called, and then our return arrow to show where the return value of this stack frame is going to go. When this method finally does return something, where are we putting that value? The return arrow tells us that. Then we're going to put the parameters on the stack inside the stack frame and assign them the values of the arguments. We only have one parameter and one argument in this example, but if we had multiple, we throw them all in this stack frame. Right at the top of the stack frame. First thing, you create a stack frame, the first thing that's going in the stack frame is always going to be the parameters, if there are any. Sometimes there might be no parameters at all, and we wouldn't put anything first step, we would just start running code. Once we have the parameters, score equals 98. Once we have the parameters in our stack frame, we're ready to run some code, and we're going to execute the body of the method. First thing we do, int tens equals score over 10. Score is an int, 10 is an int. Note that if we did 10.0, that would be a double. That would be a floating point value, and this wouldn't be the case. But since we just put 10 with no decimal, this is an int. So we have int divided by int. That's going to give us our integer division. So when we have 98 divided by 10, we don't get 9.8. That 0.8 is truncated. We just throw it away, and we just get the 9. Just the tens digit. So this variable is just going to store the tens digit of the input, effectively. Again, that's going inside our stack frame because the variable is declared during this method call. And worth noting, when I add a frame to the stack, like I just draw the box right away. When I'm doing it on the slides, that's because when I do the slides, I do the entire memory diagram, and then I back it up and then start building it one at a time for a slide. So I know exactly how big my boxes should be. On your memory diagrams, it's not going to be the case. Not always going to be the case. You can always look ahead and plan ahead and stuff. But when I'm drawing these by hand, I'll just draw the top of the memory, the stack frame. And then once I'm done with the stack frame, the method returns. I know I'm done with it. Then I'll cap off the bottom. But just a symptom of me doing these on slides. I get to plan ahead. So if you see anything like that, like you don't have to draw your whole box when you're doing these by hand. It doesn't always make sense. Because you don't know how many variables are going to be there. Especially when we're declaring a variable inside a loop. You don't know how many times that loop is going to execute, so how do you know how big to make your stack frame? You don't know how many times that loop is going to execute. Unless you read the whole code, go through the entire program, and then go through it again for your memory diagram, which I don't recommend. Just go through it once. All right, so we get tens inside the stack frame. We hit the conditional. We evaluate the Boolean expression tens greater than or equal to 9. Tens is 9, so this evaluates to true, and we execute this code block. Code block says return A. Whenever we hit a return statement, the method ends. Everything's over. Method's over. We're just going to return A. We follow the return arrow, and we get A in result. It gets the return value. And then since we returned, the method ends. When the method ends, the stack frame is destroyed. The computer actually deletes these variables from memory. Everything within the stack frame, everything about this stack frame is deleted. Score and tens, this 98 and the 9, they no longer exist at all. We cannot access them. When we get back to the main method, if we want to ask the computer, hey, wait, what was the value of scores in that last method call? It cannot tell you because that variable no longer exists. In our memory diagrams, we reflect this by crossing out the stack frame. That means this no longer exists. It's not in memory anymore. It's not on the stack. It's not part of the program anymore. It's just gone. Crossed out, that means that thing is gone. It's no longer in memory. And we print A to the screen. The print statements are the easy ones in this example. Any questions so far? So far, most of this we've seen on Wednesday already, except the conditional, of course. Moving on. All right, we're going to call this method again, call letter again. You see my stack frame's bigger. That's just because I know I'm going to have a third variable declared for this execution, for this method call. So create our stack frame, name of the method, return arrow is going into result, which already is on the stack. It does exist already, so we're just going to have an arrow to the existing variable instead of putting a new variable on the stack. Whenever you declare a variable in Java, which means create a new variable, we're going to put the type of the variable. If you don't put the type of the variable, that means we're not declaring a brand new variable. Result without a type means we're using the variable named result that already exists. But if you want to create a new variable, you have to specify the type. So that's how we distinguish between them. Just like putting const or let in JavaScript, that says, I want a new variable. And then when you use it, you don't put const or let again. One difference, I believe JavaScript lets you do it. Java will not let you put like string result right here. You can't do that. It won't let you. It'll say you're redeclaring a variable that already exists. Doesn't work. So you can only declare once. You declare the variable once, and then you can reassign it as many times as you want. But you don't declare it again. So we're going to call this method again. We get score 75. We get 7.5, or at least we would if this weren't integer division. The 0.5 is deleted. It's gone. So we just get 10s equals 7. Our first two conditionals are false. 7 greater than or equal 9, 7 greater than or equal 8. So we move on to the third one. We're going to get true, and we're going to execute this code block. Now we have our next new thing with memory diagrams, a code block. Now we executed a few code blocks, but this one's a little bit different because we have a variable declared inside the code block. Whenever we have a variable declared within a code block, that variable is treated differently than other variables declared outside of the code block. And we denote that by putting a dashed box for our code block, and then any variables declared within that code block, where a code block is any pair of braces defines a code block. I forgot to mention that one earlier. Any pair of braces defines a code block. So this is a code block, this is a code block, this is a code block. And methods are actually code blocks too, but they're special code blocks that create stack frames, so we put solid boxes for those ones. For this code block, we have result declared within it. So we're going to put it inside the code block on our memory diagram. Now we draw these as dash boxes because these aren't as strong as stack frames. We can sometimes cross this box and sometimes can't. For our purposes now, we can always cross it. We'll see examples where you can't cross. Actually, we might not even see an example where you can't cross it. Paul and I changed the content a little bit to kind of avoid that one. But I probably won't resist. I'll show you at some point. But we can cross this box, meaning when we're inside this code block, we have access to score in tens and result. The big difference, the reason why we draw these code blocks, is after the code block ends, any variables declared within the code block are destroyed. Just like the end of a stack frame, this variable result, once we hit the end of this code block, would be removed from memory. In this example, we're just going to return before we get to see that anyway, but we will have examples, lots of examples where that happens. I just want to give you your first taste of a dashed box today. So we can access score in tens. It's not like a stack frame where you cannot cross the lines of a stack frame. We cannot access result that equals A at this point. And notice that we actually have two variables named result on the stack. We reused a variable here, result C, equals C inside this code block, inside this stack frame, and result equals A outside of the current code block. And this is perfectly valid. We can reuse variable names if they're in separate code blocks. In this case, when they're in separate stack frames especially. So since this stack frame can't be crossed, we can't cross this line, and we're inside this stack frame, we can't access this variable anyway. So when we say return result, we have to mean this variable because we can't reach this one. Can't reach it at all. So we have to mean this one, and there's no ambiguity. Java knows, oh, you have to mean this result because you literally can't mean that one because it's outside the code block. I keep doing that. Outside the stack frame. It's outside the stack frame, so I can't reach it anyway. So you can't have meant that one. So we hit the return statement. We return C. We return result into result. Replace the value. And just like our code blocks, when we reach the end of a stack frame, we cross it out to show that any variables declared inside the code block are removed from memory. In this case, we ended the code block and the stack frame at the same moment when the method returned. So we're going to cross both of them out. We're going to cross out the code block at the same time we cross out the stack frame because both were removed from memory simultaneously. But we would, and we will in the next example, cross out the code block independently once we reach the end of that block. We're going to print to the screen. Let's do it one more time. Why not? So we're going to do this again, call it with 30. All of the Boolean expressions are false, so we fall back to our else. Again, I assume you're familiar with that from 115, the concept of a conditional block. We hit the else. And notice on the first example and on this example, when we hit that code block, we didn't draw any dashed box. If you don't declare any variables within a code block, there's no reason to draw your dashed box. It would just be an empty box. So why bother? Let's not do it. If you put your empty dash boxes on your memory diagrams, it's not going to be any penalty to you. You'll get your points just the same. It is more clear if you draw the empty dash box. It's very clear to us that you know what you're talking about if you add them, but they are optional. I'll never put them on the slides. In my memory diagrams, I'm not going to add the dash box for a code block for which no variables are declared within the code block. Just be an empty box. Let's just not. We don't have to. We do several things like this to reduce the clutter of our memory diagrams. As we get throughout the semester, there will be memory diagrams where I really struggle to fit the whole thing on the slide with the code. They get big, they get messy. Let's reduce the clutter wherever we can. Print again and program ends. I don't have anything really new to say with that third method call. It's another method call. It's the same thing. Any questions on this one? Does Java have global versus local variables? Since we have two result variables. So both these results are local variables, but they're local to the code block in which they're declared. So there is always a code block for the main stack frame. Sorry, I did this last lecture too. I keep saying code block when I mean stack frame. The main method actually does have a stack frame of its own. So the entire memory diagram, like this result, is in the stack frame for the main method, but we don't draw the stack frame for the main method in our memory diagrams. Again, clutter. Plus, it gets really awkward if we declared a variable here, then this variable and this variable would both be in the main stack frame, but they're kind of separated from each other. So we just don't draw the box for the main stack frame. So this result is local to the main method's stack frame, and this result is local to the letter stack frame of this specific call of the letter method. Java does not have global variables. The closest we can get is a public static variable in the class. For anyone who this doesn't make sense for, it's fine. I'm just answering the question in chat. This is beyond what we're talking about right now. But if I put a variable outside of the methods in this plus minus, if above this method call of letter, I put public static string hello world equals hello world, that would be a public static variable, which is the closest Java has to a global variable, which isn't very global at all. It's accessible from anywhere in your code, and there would only be one of them in existence. But we wouldn't have the usual issues of global variables with naming conflicts and things like that because it's specific to that class, to the plus minus class. So a variable declared in the same way in another class would not have a naming collision and wouldn't have issues with that. But that's the closest we can get to a global variable in Java, which I always recommend don't use global variables. Global constants are fine. Global variables are almost always bad. They'll catch up to you eventually. Yeah, you can write the main method before the other methods. The order of the methods doesn't matter. So if I swap these two and define main and then letter afterwards, everything's perfectly fine. But by convention, just by standards, just by programming communities deciding this is the way we should do things, the main method should be your last method in your class. So mine will always be like that. I'll follow convention, but it's going to compile and run just fine if you have them in the other order, which is not true for other languages. Some languages, you have to have the main method last if it calls the other methods. Java's fine with it. Yeah, I'm still trying to wrap my head around this other question, though. I think I either answered it in what I said earlier, or I might be misunderstanding the question. An inner or outer stack. Oh, no, that's an answer to the other question. I'm just really reading it wrong. I believe. If I'm wrong, follow up. All right. Let's go for some loops. The while loop, the notorious missing loop of 115. Let's do it right away. So while loops are pretty simple. It wouldn't be too much to add to 115, but it'd just be like one more thing. Enough students struggle with 115. That's just one thing that we remove to try to not overwhelm them. But I don't have my .0 in this one either. Got to update this slide too. So a while loop is very similar to a conditional, except it keeps executing as long as the condition is true. So when we reach the while loop, we're going to check the conditional. This has to be a Boolean expression. If it's true, we execute the body of the loop and then check the conditional again. If the conditional is still true, we execute the body of the loop again, then check the conditional again. If the conditional is ever false, then we skip to the end of the loop, the end of the body, and continue on with our program. That's a while loop. That's it. Note that a while loop and the next loop we see, a for loop, doesn't have to run at all, and every loop that you see in 115 actually, doesn't have to run at all. So if the condition is false when you first reach the loop, the body of the loop never executes ever. This is a common mistake in 115. This is a common mistake in 116 still, is if you have a return statement inside a loop, for while loops, for loops, any type, for each loops, any type of loop, you have a return statement inside a loop, and Java gives you some error that says, hey, you told me you were going to return an int, and you returned void. You didn't even give me anything. And then you say, I have a return statement right there in my loop. What the hell? Well, there's no guarantee that your loop is ever going to execute. If the condition is false when your loop is first reached, it just skips over the loop. And if you have no return statement after the loop, Java's going to be mad at you. It's going to say, if this loop never executes, you don't return anything. Even though you always return something if the loop executes, that's not good enough. Same as with your conditional, like in the previous example, if we didn't have an else statement on that, and all the conditions were false, then we would never return anything, and Java would have a problem with that. Even if our last one was else if 10's less than 7, I'm trying to remember the exact numbers, else if 10 less than 7, even if that was the code, or 10's less than 7, yeah, I said that right. Even if that were the code, and we as humans can look at it and say, well, it's always going to return one of those. One of those has to be true. Same with the loops. If we have a loop that we know is always going to execute, Java's still not happy with that. Java's going to say, well, I don't know, I'm still not convinced. What if it doesn't? So you always have to have some return statement outside the loop as well, even if you have a return statement inside the loop. Probably a mistake. I think we all make that mistake. Probably a mistake you made in 115 at least once. Trying to return inside a conditional, things like that. Using a variable after a code block ends, not knowing that that value was destroyed from memory. Common thing as well that we're looking into here. All right, that's while loops. I just got 2 slides on those. For loop is similar to a while loop with some extra stuff. You've seen these last semester. You've seen these in JavaScript. Ever so briefly, I believe you move right on to for each loops pretty quickly. But you've seen these for loops. This statement is going to be a Boolean expression which behaves just like a while loop. So this loop is going to loop as long as this Boolean expression resolves to true. Then run the body of the loop. We're also using a little bit of shorthand. I'll explain the other 2 statements in a second. But we're using a little bit of shorthand, and we used shorthand in the previous example that I'll talk about when we get to the memory diagram. But we're using this x plus plus. This means increment plus. This is equivalent to saying x equals x plus 1. So we're going to start using shorthand. We avoid the shorthand in 115. Again, we don't want to just throw too much stuff out there in the first semester. 116, y'all can handle it, and you're ready for some of these shortcuts to save you time, save you frustration, not frustration, but save you time, save you typing. X plus plus, instead of typing out x equals x plus 1 every time, saves us some keystrokes. And there's 3 statements to define a for loop that are separated by semicolons. First is the initialization statement. This statement runs exactly one time. When we first reach the loop, we run the initialization code. And this is usually where we're declaring a variable, which will be our iteration variable. Boolean expression, we already talked about. That behaves just the same as a while loop, which behaves very similar to an if statement, except it loops multiple times. And then increment, this statement is ran every time we reach the end of the loop body. So note that the increment statement might never be executed. If the Boolean expression is false when we first get to the loop body never executes, the increment statement never executes, and we just move on with our program. So something to keep in mind. And with that, let's memory diagram this thing. So in here I got my point oh. I didn't explain what I was kicking myself over a second ago. I have to update the previous slide. But I like having 10.0. It just makes it very clear that this is a double value. Before I had double val equals just 10 without the 0.0. And it's perfectly fine. It's valid code and everything. I just like to be explicit, especially in my slides when I'm showing this stuff, a lot of this stuff for the first time. I want to be explicit in my conventions. So we're going to... I put 10 right here, 10.0. Jesse, come on. So we're going to declare val, give it the value 10, put that on our stack. And notice I know there's going to be a lot of things printed to the screen, so I move my in-out up. We're still not using the heap, so I'm going to have more space for my in-out. Just organizing things a little bit. And let's hit this while loop. So we hit the while loop, we're checking the conditional. Is 10 greater than 1? Here, the same doesn't apply. That 1 is an int, and that's perfectly fine. I want that to be an int. It wouldn't change the behavior of this code at all, but just to have an example of what I'm about to say, we have a double, and then we're comparing it to an int. This is valid in Java. In most cases, you can't mix types, but since these are 2 numeric values, Java will take that int, take the value 1, convert it to a double, not the value itself, but it'll create a copy of it, convert that to a double, and then use that value for the comparison. So it'll say, okay, you said 1 is an int, I'm going to convert that to 1.0 as a double, and then compare 10.0 to 1.0. So mixing doubles and ints a lot of times does just work for us, which why I got away with that in the other slide. Just equals 10 is fine. I updated the repo and forgot to update that image, but not image, these aren't images, but forgot to update that code. So 10.0 greater than 1, true. So we're going to execute the body of the loop. Body of this loop is going to print val to the screen. Val was 10.0 at that moment. So print that to the screen, and then val slash equals to, this is our next bit of shorthand that we're going to see. We're going to use pretty extensively throughout the semester. Paul and I both really like this syntax. We're going to use it a lot. And I think most developers like it. Once you start using it, if you haven't already, a lot of you use it in 115, you'll start using it a lot. Val slash equals 2, this is shorthand for val divided by equals 2, which is shorthand, which means val equals val over 2. So we're going to divide val by 2, and then reassign the result back into val. Again, just saves us some typing. We don't have to type the variable name twice, especially you got really long variable names. You don't want to have to type them twice. Just saves us some keystrokes. Same thing for plus equals. Plus equals and star equals are the 2 we'll use the most. Probably plus equals the absolute most. Minus equals also exist. Same thing, same concept, except it's going to add, subtract, multiply the variable, and then reassign to that variable. A little bit of shorthand that you're ready for in 116. And here we have division, we have 10.0 as a double divided by 2 as an int. Remember, our integer division was when we had an int divided by an int. In that case, it was integer division. We only got the whole number portion. If they're not both ints, we do get floating point arithmetic. So since 10.0, since val is a double, we have a double divided by an int. And Java's going to do the same thing it does with this comparison. It's going to say, okay, you have a double divided by an int. Let me convert that int to a double and then divide two doubles. So we do get 5.0, not 5 the int. We get 5.0 the double. And we loop around for a while. 5.0 is greater than 1, true. So we're going to print 5.0, divide, and we do get 2.5. We don't truncate this to 2. Even though there is an int involved, one of the values is a double. Therefore, we're going to get a floating point answer. 2.5 is still greater than 1. Let's keep going around. We're going to print 2.5. We're going to divide that by 2. We're going to get 1.25. 1.25 greater than 1. This is still true. We're going to loop again. Let's just keep going through. Every time we update a variable, we're going to cross out the old value and write the new one as many times as we update the variable. Print 1.25, divide, we get 0.625, and then finally we hit our conditional again, check it again, 0.625 greater than 1 is now finally false, and we can finally end this loop. So this loop ends. Once this condition is false, we do not execute the body again, and we go right after the closing brace and pick up with our program and start executing code after the loop. Now notice that val is still on the stack. Val was declared outside of the loop, outside of that code block. There were no variables declared inside the code block for the while loop, so we didn't even bother drawing our dash line for that code block. And remember, a code block occurs whenever we have braces. That's going to be our conditionals, our while loops, our for loops, our for each loops starting Monday. And even if we won't do this in 1.16, but you could create a code block without any of those. You could just slap some braces in your code and create a brand new code block. And there's almost no reasons to, but it is legal. It is valid code. So whenever you see braces, that's a new code block. No variables declared in the code block, so I didn't draw it. But val, even though it was, intuitively, like to us humans, we look at this and say val is highly related to that loop, and we're not using it after the loop. We would kind of think that might go away. No, it's declared outside the code block, so it's not destroyed. The same won't be true for this for loop. There's no variables declared explicitly in the loop of the body, in the body of the loop. But any code for the initialization statement is executed inside the code block of the loop. So any variables declared here, even though it's technically outside the braces physically, it is part of the loop. It is part of the code block of the loop. It will be declared inside the loop's code block. So x, the iteration variable for this loop, is part of the code block for the loop. Check the conditional. 0 less than 5 is true. Run the code. It just prints 0 to the screen. And then when we reach the end of the body of the loop, we execute the increment statement. So we bump x up by 1, cross out the 0, write a 1. Do it again. Condition still true. Run the body of the loop. Increment. You get it, right? So at the time when we print 4 to the screen, same thing, print 4. We get to the end, we're going to increment x up to 5. We're going to check our condition again. 5 less than 5 is finally false. We finally get to exit this loop. And when we end the loop code block, we cross out that code block. So x is no longer on the stack. The variable x does not exist. This is, again, one of those common problems in 1.15 where right here you might want to return x if this were a separate method call and not the main method. You might want to return x or set y equal to x plus 7, whatever you want to do with this value. And it keeps saying variable not found. And you point to your code and you say, it's right there. X is right there. What do you mean it's not found? It's because it doesn't exist anymore. It was declared within the code block of that loop. That code block has been erased from memory because we hit its closing brace. So X does not exist. As far as the computer is concerned, it never exists. The computer's not going to look through history, look through things it already deleted and say, oh yeah, there was an X. Yeah, maybe you meant that. No, X is gone. It's not in memory anymore. The computer has no idea that it ever exists. The computer completely forgot about it. It's not in its memory anymore. And that's some common errors in 115, like I mentioned. But you're beyond that, but this is exactly why that's happening. We hit the end of the code block disappears, erased from memory, doesn't exist. Then we hit the end of the program ends. Can you explain why you use the dash box for X variable? So solid boxes are for stack frames. That's only related to method calls and always related to method calls. The dash box is for code blocks. Whenever we hit a code block where we have a variable declared in that block, we'll use a dashed box. These are like semi-permeable. Inside this dash box, when we're executing inside this for loop, we still have access to val, which is outside that code block. So we can cross these lines. But once the code block ends, anything declared inside that code block is destroyed. We technically had a code block here for the while loop. So we could draw our code block here, but it would be an empty dashed box because we didn't declare any variables in it. So we just say there's no point in drawing an empty dashed box and then crossing it out. Let's just skip those steps. But technically there could be another one there. It'd be just as correct. Yeah, if it was print instead of print line, you would just be missing the line breaks here, and these would all be printed on one line. Paul and I were not all about tricking you like that, so we won't throw that at you on a quiz. We won't say, gotcha, it was print instead of print line. You didn't see that ln missing? Ha 0. We don't do that. We don't play those games around here. But technically, yes, that's what would happen. All right, any other questions? Did I miss anything? How do multi-line comments work in Java? It's / star and then * / to close it. Okay. Forget if I mentioned this last time, but I'll do lecture questions at the end of lectures, and once you answer the question, you're free to go. I have nothing else after I do the lecture questions. So have a great weekend. I'll see y'all Monday. Try to stay warm out there.